Hi, everyone. Today we are going to talk about the assignment problem. The transportation problem that we discussed last time. The assignment problem is also a very well studied traditional example of the linear programming model. And it is also one of the fundamental combinatorial optimization problem in the branch of the operations research in mathematics. So let me first share my screen. Okay, so the goal of the assignment problem is to assign a number of resources. Usually that can be the workers or the machines to an equal number of activities or tasks, while minimizing the total cost or maximizing the total profit of the allocations. And finding the best person or machines for a job would be an apt description of the assignment problem. And the best means that the least cost way of assignment, okay? Okay, so the problem of assignment arises because available resources such as man, machines have varying degrees of the efficiencies for performing different activities, right? So the cost, profit, or the loss of performing the different activities is also different. And the assignment problem is definitely a highly useful tool for the operation and project managers for optimizing cost. In general, the assignment problem can be described as follows. So we consider a certain number of resources and the same number of activities, okay? And the objective is to minimize the total cost of assigning every resource to an activity. So as a general rule, all the jobs must be performed by exactly one worker, and every worker must be assigned exclusively to one job, right? So in this cost matrix, the total number of rows is equal to the total number of columns, okay? And the element C sub ij represents the cost of assigning the machines or the workers, number I, to the job number J in a job example for example, okay? And the assignment problem is the actually special case of the transportation problem, where the machines represents the sources and the jobs represents the destinations. And also the supply amount from each source exactly equals 1. And the demand amount from each destination exactly equals 1 as well. And the assignment problem can be solved directly as a regular transportation problem. However, the fact that all the supply and the demand amount from each source and destinations are equal to 1 has led to the development of a simple solution algorithm called the Hungarian algorithm. And we are going to learn about it later today, okay? Okay, so using the binary integer decision variable the assignment problem can be formulated like this. Okay, so the decision variable, binary decision variable, x of ij equals 1 if the resource number I is assigned to jobs or activities number j, and 0 values otherwise. And the objective is to minimize the total cost of assigning every resource to an activity. And please keep in mind that the assignment problem is a special case of the transportation problem with supplies and demand from each source and destinations equal to 1, right? So the first set of constraints ensures that each resource is assigned to exactly one activity, right? And also second set of constraints ensures that each activity is assigned exactly one resource, okay? Oh, okay. This is, okay, what I told you already. And the assignment problem has two important properties. Given the cost matrix like that, for each row, exactly one assignment is made because each resource is assigned to exactly one activity, right? Likewise, for each column, exactly one assignment is made since each activity is assigned exactly one resource. I'm just repeating this because that is quite important, and that's the one very big thing that can be distinguished from the transportation problem. So please keep in mind that, okay? Okay, anyhow, so therefore, the first property of the assignment problem is that if a number, the delta, is added to or subtracted from every cost in a certain row or the column of the matrix C, then every feasible set of the assignments will have its cost increased or decreased by the same amount, delta. But the optimal set of assignments remains optimal. So for example, if we add the delta value to row number 1, then the total cost is also increased by delta because the delta value is independent of the decision variable x, okay? And the second property, another property of the assignment problem is that if all of the assignment costs are the non-negative, and if there is a set of the assignments with total cost equal to 0, then that set of assignment must be optimal, okay? So we are going to talk about this very soon, but as of now, I'd like to let you know that the Hungarian method solves the assignment problem by just adding and or subtracting certain amount in each rows and or columns until the zero cost assignment is found, okay? So I would say the finding the zero cost assignment would be the goal of the assignment and of the Hungarian algorithm, okay? Okay, now let's take an example. So in this example, we consider 4 different machines to process 4 different jobs, okay? And the processing time for each machine job assignment is shown in this matrix, okay? Then our question is, what is the assignment which will minimize the total processing time. Okay. So to do that, to find the zero cost assignment, let's subtract. First of all, let's identify the smallest cost from each row. And then subtract the same amount from each row. Okay, and this introduces at least 1 0 values into each row, right? So for example, here, 4 is subtracted from each cost in the first, second, and third row, because 4 are the smallest cost, right? In each row, here and here. But 3 is subtracted, right, from the last row, because 3 is the smallest value in the fourth row. And this process is called row reduction. Next is the column reduction. Likewise, for each column, we need to identify the smallest cost. Okay, and then subtract the same amount from each column. Okay. Of course, if a column already has a 0, it's not going to be changed, right? So here, first, second, and the fourth column already has 0 values in it, right? So 0 would be the smallest cost in this column number 1, 2, and 4. So after the column reduction, the first, second, and fourth column remains the same, okay? And in this case, only the column number 3 lacks a 0. So only column number 3 is reduced after the column reduction. Is that right? Okay, after the row reduction and column reduction, if you examine the resulting cost matrix, then actually we can find an zero cost assignment, the assignment with a total cost equal to 0. Okay, that is what is called zero cost assignment. Okay, so in order to identify the zero cost assignment, what you need is to identify the 0 value that appears only once in each columns or in each row. So in this case, this 0 appears only once in the last column. So we need to pick this, okay? And then after that, we cross out the same column and same row to prevent from further assignment in the same rows and same column, okay? And then after that, we repeat the same thing, identify 0 value that appears only once in each rows and column. I believe this is the one, right, that appears in the first column. So we need to choose that and then cross out. Now we have 2 different choices. So in this case, if you go with this, then you have to go with this, right? But if you go with this, then you have to go with this, okay? So it's up to you. In this case, you can just arbitrarily choose either of 0, here or here, or here or here, okay? And this is the resulting zero cost assignment, okay? So in this case, the machine A has to be assigned to job number 1, right? That's why we have here. Machine B has to be assigned to job number 2. And machine C, job number 4, machine D, job number 3, okay? So these are the optimal assignment. And the corresponding optimal assignment cost would be 16. And we obtain this value 16 from this original cost matrix, okay? Corresponds to our optimal assignment. We need to pick these 4 different numbers, right? According to our optimal assignment. And then add up these 4 values, which becomes 16, okay? Okay. Okay, now let's consider this case. Sometimes, however, you cannot find a zero cross assignment after the row reduction and column reduction. So, for example, in this cost matrix, machine C cannot be assigned to both jobs number 1 and 4, corresponds to this 0 value. So one job must be assigned a machine with positive cost, right? So now I'm going to talk about the Hungarian method, Hungarian algorithm that can resolve this kind of situation, okay? And this screen summarizes the detailed steps of Hungarian algorithm. And so I gotta tell you this before you start the Hungarian algorithm, which is step number 1 through step number 4, you gotta make sure this first, okay? So you gotta make sure if the total number of rows and the columns in the cost matrix are equal, okay? If it's not equal, then the assignment problem is unbalanced or is not standardized. So in this case, the Hungarian method may yield an incorrect solution. Okay, so just make sure before you start the Hungarian algorithm, make sure any assignment problem, I mean the cost matrix should be balanced. Okay, by adding 1 or more dummy rows or the columns before it is solved by the Hungarian algorithm. Okay, and our first step of the Hungarian algorithm is the row reduction. So as we discussed earlier, we need to find the smallest cost in each row, and then reduce all the costs in that row by that amount. And the next step is the column reduction. Likewise, find the smallest cost in each column, and then reduce all the costs in that column by the same amount. Okay. And step number 3 is finding the minimum number of lines that will cover every 0 values in the cost matrix. And I'm gonna talk about this later, but the keyword is the minimum here. Okay, you have to find the minimum number of lines that will cover every 0 in the cost matrix. Okay, and then if the number, the minimum number of lines is equal to the number of rows or the column, then you gotta stop, because it does indicate that you can do the 0 cost assignment with the current matrix, cost matrix. Otherwise, you need to move to step number 4 and conduct it, and then go back to step number 3. So you're gonna repeat this until you meet this condition, okay? If the total number of lines that will cover 0s gonna be the same as the total number of rows or the column, then you're gonna stop. Okay. Okay, now let's take an example. So I've modified the our original example just a little bit. And now let's find the least cost assignment for this cost matrix. using the Hungarian method. Okay. Okay, so the first step, but before you start the first step, just make sure that you have the same number of rows and the same number of columns, which is true, right? So you don't need to do anything before you start the Hungarian method. So step number 1, row reduction. So in this case, the minimum cost, smallest cost for each row would be 4, and also same 4 down here and 3. So 4 is subtracted each cost in the first, second, and third row, and 3 is subtracted from the last row, right? So this is going to be the resulting cost matrix. And then we're going to apply column reduction to this cost matrix. So the column number 1, 2, 4 remains the same because the smallest cost for those columns are 0, right? So only column number 3 will be reduced by 1, right? The minimum cost in column number 3 is 1 down here. So this is the resulting cost matrix from the column reduction. Okay, now the step number 3 is to find the minimum number of lines. You gotta find the minimum number of lines that is required to cover every 0 element in the cost matrix. Okay, obviously 4 lines can cover every 0, but in this case 3 lines can cover every 0 in this cost matrix. Is that right? So there is no 0 cost assignment possible with this matrix. And this can be determined by the fact that the zeros can be covered with only 3 lines. Okay, and this minimum number of lines required to cover every zeros is not equal to 4. Okay, and this 4 is the number of rows or the columns, and this number 3 is the minimum number of lines required to cover zeros in the cost matrix. Okay, so we're going to move to step number 4. Okay, now step number 4 is the actually involving the creating additional 0 elements without the creating any negative elements. Okay, so notice that the smallest aligned cost is 1 here. All right, so these are the 3 lines we draw, and the smallest aligned cost is 1. Okay, so we're going to subtract the same amount, 1, from every element in the entire table. Okay, so to do that, let me open the Excel spreadsheet. Okay, and let me disable my camera. And then type in the matrix values. So 1, 0, 0, 0, 2, 0, 0, 1, and 0, 4, I think this is not the one, right? Okay, this is the one. Oh, so 2, okay, let me delete. How come I cannot delete this? Okay. So let's start over. So 2, 0, 0, 1, 3, 0, 0, 2, 0, 3, 1, 0, 2, 0, 0, 4, right? Okay. Okay, so what you're gonna do is, okay, let me first mark yellow. This is one line, and this is another line we draw, and then this is another line. So we draw 3 lines, right, to cover every zeros. And right after that, we need to identify the smallest aligned cost, right? So that is 1 up here. So we're going to subtract this same amount of 1 from every element in the entire table. So let's do that. So we're going to subtract 1 from everywhere minus 1, right? So we're going to do that like that, okay? And of course, this will create a new 0 up here, right? From 1 to 0, right? In this new location, we have 0. And then what you need to do is, in order to restore the previous 0 elements and also eliminate negative elements, we will add the same amount of 1 to each row or the column with a line covering it, okay? So I'm talking about these, all of these location, this, and then all of this location, okay? We are going to add 1 to all of this location, okay? So let me use the full screen. So we are going to add 1 to this second column, right? So we are going to add 1, this plus 1, right? And also we're going to add 1 to this column, corresponds to this line, okay? So that's going to be this plus 1. And we do the same thing for the other elements in the same column. And then likewise, we're going to add 1 to this location, right? So we're going to add 1 to this location. That's going to be this plus 1. Okay. And then this is going to be 4, right? 3 plus 1 would be 4. So we're going to add 1 here. Likewise, this value becomes 2 because we're going to add 1. And then this one should be 0, right? It's going to be this plus 1. And then we're going to just copy all the other values from this matrix. Okay, so here we have 1, 2, 1, and 3, and here 1, 0. Okay. Or alternatively, we can do this. Personally, I like this better because instead of going through these 2 different steps, we can get the same matrix of this with only 1 step. Okay, so what you are going to do is like here. Again, we're going to locate the smallest unaligned cost, which is 1 again, and then subtract this amount, this cost, from all unaligned area, and then add the same amount at the intersection of lines. Okay, so let's do that. So so our new matrix would be this 4 by 4 matrix, right? This one. So I'm gonna let me do this way. So that's going to be the area. Okay, so here we're going to have this value -1, right? And this is going to be also original value -1. And then this is going to be the same. Original value -1. Right? Actually, we don't need this column. Okay. And so here we have this value minus minimum value, minimum, the unaligned cost, right? And this is going to be 2 minus the smallest unaligned cost, which is 1, right? And here we also have 4 minus the smallest unaligned cost. Sorry, this value minus 1. Okay, like that. And then we are gonna add the smallest unaligned cost to this location, to this 2 location, right? Because that's the intersection of the lines. So this value is gonna be 3 plus 1. And then this is going to be 1 plus 1. Is that right? And all the other values remains the same. So I'm going to just copy from this matrix. This is going to be same as this, right? And that's going to be same as this. This is going to be same as this, right? And this is going to be same as this. It's going to be same as this. This is going to be same as this. And finally, this is copy from here. Okay. And then if you compare this matrix with this, you will see that those are identical. Okay. So it's totally up to you. You can go either this way or this way. Okay. For conducting the step number 4. Okay. Okay, now so this new matrix has a 0 value that is not covered by a line. So I'm talking about this 0, right? So previous time we have this line and this line, right? And this line, right? And we need one more line to cover this 0 value, right? So either you can draw this way or this way, right? So definitely we do need 4 different lines to cover every 0 element in this cost matrix, right? And this time the minimum number of lines required to cover every 0 gonna be 4. And this value is also same as the total number of rows or the columns. So we have to stop here because we know that we should be able to do the 0 cost assignment in this table, okay, in this cost matrix. So here, 0 cost assignment can be done if you choose this, right? Because that is the only 0 appears in the first column, right? So you gotta choose this. So I'm gonna mark it yellow and then cross out the same column and same row, right? And then I can see that this is the only 0 appears once in the last column, right? I'm gonna cross this out and there's 2. So we have 2 different 0 cost assignments available in this case. So you can choose either this or this, right? Or so this or this. It's up to you. So if I go with this, then you gotta stick to this, right? or if you want to go with this, then you're gonna go with this. Okay. So I believe, oh, okay. So this is the optimal solution, optimal assignment in our case. And both of these are optimal, okay? Okay, then now let's go back to our slide. Okay, so I've extracted this example from our textbook. So 4 cargo ships will be used for shipping goods from one port to 4 other ports, and they are labeled 1, 2, 3, and 4. And any ship can be used for making any one of these four trips. However, because of differences in the ships and cargoes, for example, the total cost of loading, transporting, and unloading the goods for the different ship port combinations varies considerably, okay? And they are shown in this table. And our objective is to assign these 4 ships to the 4 different ports to minimize the total cost for the or 4 shipments. Okay. Okay. So first, how do you answer for this question A? It asks you to describe how this problem fit into the general format for the assignment problem. So if you think ships are the assignees and the ports are the assignment, then this problem fits into the general format for the assignment problem, right? So that's very simple question. Okay, then let's answer for the question B. So we need to obtain an optimal solution. And let's use the Hungarian algorithm that we just discussed. So again, I'm gonna use Excel spreadsheet for that. So I'm gonna create new tab. And then I'm going to put for this table information here. So we have 500, 400, 600, 700, okay, 600, and there's 600, 7, and 5, 7, 5, 7, 6, and 5, 4, 6, 6. Okay. So here, what I'm going to do is, okay, let me just use the full screen. Okay. First of all, we gotta make sure that we have a balanced assignment problem. Check the total number of rows are equal to the total number of columns, which is true. So we can move to the row reduction, right? So we are going to identify the minimum values for each row. So I'm going to use Excel function min for this, right? And then I'm going to copy this. And then I'm going to just copy this value. Like that. And then for the row reduction, we are going to do this minus this, right? So the first column, the first row is done. And then just copy the formula and paste it, right? Drag it. Then our row reduction is completed. So this is the resulting cost table, right? So I'm gonna copy this to down here. And then now I'm going to identify the minimum cost for each column to conduct the column reduction. So this time, that's going to be the minimum values for each column, right? And then I'm going to just copy from it. Okay, and then this value is going to be this minus this, right? So the column reduction for first column is done. And second, third, fourth column is also completed, right? Okay. Now we need to identify the minimum number of lines that can cover every zero element in this cost matrix. So how many lines are required? Minimum number of lines. I believe in this case, we need 4 lines to cover every zeros, right? 3 is not enough. So it's got to be 4 different lines. And this number 4 is equal to the number of rows or the number of columns. So we got to stop here because we should be able to do the zero cost assignment on this cost matrix, right? So we have to choose this for the zero cost assignment because this 0 appears only once in the last column, right? So I'm going to mark it yellow and then cross out. Same column and same rows. And there is tie, right? There is no zeros, appears only once in each rows and column. So if there is a case, you just need to arbitrarily select any zeros. So I'd go with this. And then make sure you're gonna make sure to cross out same rows and columns. Again, there is ties. So you'd have 2 different choices in this case. You can go with either this and this, or this and this, right? So let's go with this then. Then we're gonna remove this, right? And then finally, we're gonna choose this. Okay. So this is the optimal assignment, right? Okay, so what you need is go back to the original cost matrix. Oh, we already have here. So I mean, you need to look at this, okay? Original cost matrix, and then mark it where the optimal assignment occurs. So here and here, here and here, right? So I'm gonna mark it with green this time. The optimal assignment would be shift to port, right? Ship number 1 goes to port number 1, right? 1. And the, let's say, optimal assignment cost would be 500, right? Plus. So 500 corresponds to the same location here, right? This one or this one, right? And then ship number 2 goes to port number 4, right? Which is here. And the corresponding assignment cost would be 500. So I'm gonna add another 500 here. And then ship number 3 is gonna be assigned to port number 2, right? And we have to add another $500 from here, right? And finally, ship number 4 will be assigned to port number 3. And the corresponding assignment cost would be 600. So it has to be added here. Okay. So how much is the optimal assignment cost? That's going to be 2,100, right? Okay, so this is it. So if I ask you to solve this problem using the Hungarian algorithm, then you have to report this together, okay? You need to identify optimal assignment and the corresponding optimal assignment cost, okay? Okay, then let's go back to our slide. Okay, I think this is the last example for today. Okay, so in this example, a coach of an age group swim team needs to assign swimmers to a 200-yard relay teams to send to the Junior Olympics because most of his best swimmers are very fast in more than one stroke. It is not very clear which swimmer should be assigned to each of the 4 strokes. The 5 fastest swimmers and the best times they have achieved in each of the strokes summarized in this table. The coach wishes to determine how to assign 4 swimmers to the 4 different strokes to minimize the sum of the corresponding best times. Okay, so we can nicely solve this problem using the Hungarian algorithm. Okay, so let me put these values to my Excel spreadsheet. 37, 35.4, okay, and 43.4, 33.1, 42.2, 34.7, 41.8, right? Okay. 33.3, 28.5, 38.9, 30.4, 33.6, 29.2, 26.4, 29.6, 28.5, 31.1. Okay, let me double check before we move further to make sure all of these values are correct. Okay, looks like these are all correct. Okay, now let's implement the Hungarian algorithm to this cost matrix. But before you do that, one thing you need to make sure if this given cost matrix is balanced or not, okay? So the total number of rows in this case is 4, but the total number of columns are 5. So this is not a balanced assignment problem, right? So what you need is to add one more row, one more dummy row with all of the cost values equal to 0, okay? So that is necessary step, okay, before you start the Hungarian algorithm, okay? So make sure the total number of rows and the total number of columns are equal, in this case 5 each, right? Okay, now we are ready to implement the row reduction step. Okay, so as before, we need to identify the minimum cost for each row. Okay. And then I'm going to copy this value to the other elements in the same row, okay? Like that. Okay, in a way, I can conduct the row reduction. That's going to be this value minus the minimum value, right? And then we're going to do the same thing. So the first row is done, and then the other rows also completed, right? Now we need to move on to the column reduction, but the column reduction is not necessary, right? Because you can see that every column has the value of 0. And this value 0 is going to be the minimum cost, right? Minimum value from each column. So every column remains the same after the column reduction, okay? So what is the next step? Next step is step number 3. We need to identify the minimum number of lines that will cover every 0 values in the cost matrix, okay? And it's very easily seen that there is no 0 cost assignment possible in this cost matrix, right? Because we just need 2 lines, right? Which is this line and this line, right? So all of the 0 values can be covered with only 2 lines, right? So this number 2 is not equal to the total number of rows or the columns, which is 5. So we need to conduct the step number 4, okay? So step number 4 is to identify the minimum aligned cost. So where do we have the minimum aligned cost? It's going to be this, right? 0.9. 0.9 is the minimum aligned cost. So what you are going to do is subtract this amount from the aligned area here, and then we're going to add this amount to the intersection of these 2 lines, okay? So here, this plus 0.9, right? And also, we're going to do the same thing, right? And here, oh, I just need to copy the formula to here, right? So in a way, just make sure 4.7 down here plus 0.9 is going to be 5.6, right? 5.1 plus 0.9 is going to be 6. Likewise, 3.2 plus 0.9 would be 4.0, 4.1, right? So that is correct. Now we need to add 0.9 to this location, right? That's going to be this plus 0.9, minimum aligned cost. And all the others remains the same. So these are all equal to these values, and these all equal to these values, okay? But these are from the previous matrix. So I'm gonna just copy. Like this. Okay. Okay, so this is the resulting table. And now we need to do the step number 3 again, okay, which is identifying the minimum number of lines required to cover all of the zero values in the cost matrix. So how many lines do we need? I think, oh my gosh. Sorry, I made you confused. I did wrong. So here, instead of subtracting, I did addition, right? So you are supposed to subtract the minimum aligned cost from all aligned area and add the cost in the intersection of the lines. So actually I made a mistake here. So instead of adding 0.9, I have to subtract it, right? So 4.8 minus 0.9 gonna be 3.9, right? So I have to do this. And then I'm going to make this. So actually this value is 0, okay? 0.9 minus 0.9 is 0. So let me just do this. Okay, I think this is the right cost matrix then, because I can clearly see that there is one more 0 appears, right? Compared to this matrix, right? That's the main purpose of doing the step number 4. So as of now, we do need 3 lines. So 1, 2 lines, right? And you can draw either this line or this line. It really doesn't matter, okay? So I'm gonna just draw this line then, okay? And then again, step number 4, what is that? We need to identify the minimum aligned cost, right? So I believe that's gonna be this 0.7. So I'm gonna mark it with red. So as before, what you need to do is subtract this amount from every aligned area and then add this amount to the intersection of these 3 lines, okay? So let's do this. So I'm gonna first add this amount to the intersection of these 3 lines. So I'm gonna add this. So this plus 0.7. And down here, this is gonna be this plus 0.7. Okay, so make sure 0 plus 0.7 would be 0.7 here. 0.9 plus 0.7 is 1.6, right? Okay. And then here, 9.4 minus minimum aligned cost, which is 0.7. And then I'm gonna copy the same formula and paste to here, okay? Again, this is gonna be 0 because we know that 0.7 minus 0.7 is gonna be 0. and all other locations remains the same. So I'm just gonna copy from the previous. So I'm just copy this, and this paste. Okay, I think. Okay, so this is the resulting table, cost table. And again, now we need to identify the minimum number of lines required to cover every zero. So previous time we do require 3, but this time how many lines do we need? So we do need 1, and 2, and 3, and 4. So we do need 4 different lines, okay? Okay. Sorry, this morning I have several times the visitors coming in, so my lecture recording has been interrupted a couple of times. So where was I? Okay, so it looks like we identified the 4 lines can cover every 0 element in the cost matrix, right? So I'm gonna write down 4 lines. Okay, but this number 4 is not the same as the total number of rows or the columns that we have, right? So which means 0 cost assignment is not possible at the moment. So again, we need to identify the minimum aligned cost. So that's gonna be 1.2, right? So next, what you are going to do is subtract this amount from the aligned area, and then add this amount to the intersection of these 4 lines. So those are these 3 different locations, okay? So let's do that. So here we have this value minus minimum aligned cost, which is 1.2. And then I'm gonna add, I'm gonna copy this. Oh, not here. Should be here, right? Okay. And then add the same amount. That's gonna be this value plus 1.2, right? And then just drag it. And all the others remains the same. So this is gonna be this. And then this, right? Again, copy this, paste here and here, okay? Okay, now we need to identify the minimum number of lines that are required to cover every 0 element in this cost matrix. So how many lines are required? The minimum number of lines. It looks like we do need 5 different lines, 4 lines cannot cover every 0 values. So right now we do need 5 lines. And this number 5 is equal to the number of the rows or the columns in our cost matrix. So now we should be able to do the 0 cost assignment on this cost matrix. Okay, so let's do that. So let me copy this. Okay, make sure we have the same, exactly same values, right? From here. So in order to the 0 cost assignment, you need to identify the 0 values that appears only once in each rows and or columns. Okay, so this one, this 0 appears only once in the first row. So I'm gonna pick this. And then cross out the same rows and same column. And then this one, right? This 0 appears only once in the last column. So I'm going to pick this and then cross out this. And this appears only once in the first column, right? So I got to pick this. And then cross this out. And this 0 appears only once in this column and then in this row, right? So I'm going to pick this. Then cross this out. And this is what is left over. So I'm gonna like this. Okay, so this is the optimal assignment, okay, in our problem. Is it the one? Okay. So optimal assignment would be what? So let me go back to our problem description. What is that? Okay, this one. Okay. So here, optimal assignment is backstroke David, right? And breast stroke would be 20, right? And butterfly, Chris, and freestyle, hard, right? And Ken's gonna be the standby, right? And the optimal time, let's say the best time for this assignment would be summation of this value, this value, this value, this value, and this value. Okay. That's going to be this summation of this, 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 and this. So it's going to be 126.2 seconds. Okay. So that's the optimal solution that you need to report. Okay. Okay, so this is all for today. And next time, I'm going to give you several more examples for both transportation and assignment problems. Okay. And then after that, we're going to move on to the new topic. Okay, thank you. Bye-bye.